So for question 11, we have two distinct lines, L1 and L2, and they intersect at point P. So you can have multiple different versions of this. This is L2 and this is L1, and then they all intersect at point P. But L1 also has 4 other points drawn out, and L2 also has 3. So there's a lot of different versions for how you can have points, but I just drew 2 examples here. So letter A1 asks for how many different numbers of quadrilaterals that could be formed. So obviously a quadrilateral has 2 points on each side, has 4 vertices. So on one line you're going to want to find 2 vertices, and even if you have 3 here, these endpoints are ultimately the 2 vertices. And on L2 you also want 2 vertices. So it's a combination problem. You have 4 choose 2 points and then 3 choose 2 points from L2. When you put those into your calculator and add them together, you get 9. And then for part 2, you have actually this is a non-calculator problem, so you could probably figure that out using your formula packet, but it still equals 9. And then for part 2, you have to find the different number of triangles that could be formed. So you have any 2 points on L1 and then 1 point on L2, or you could also have just 1 point on L1 and 2 points on L2, because the triangle has 3 vertices. So you add those 2 different possibilities together, you get 16. So for part B, it gives you the vector equations of the lines, and you have to verify that the point P is where they intersect. It gives you the coordinate for point P. So we put these in their coordinate form here. So we have x equals 1 plus lambda and so on for L1, and then L2 is very similar. And so where they intersect, the x and y and z values are all going to be the same. So we set these equal to each other. And you find that 2 lambda equals 6 mu for the y values. So that way you can find, when you divide by 2, you find that lambda equals 3 mu. You plug 3 mu in for lambda, I did for L1, and set them back equal to each other. Found that mu equals 1. So then you can plug in mu for L2 back up here again, find the x, y, and z coordinates, and they do intersect at 4, 6, 4, because when you plug mu in, x, y, and z equal 4, 6, 4. So P is where it intersects. Okay, part C. In part C, it gives you the coordinates for A and tells you that it lies on L1, and that you need to write down the value of lambda corresponding to point A. So you have point A equal to 101 plus lambda plus the direction vector. So you can also put this in the coordinate form here, have the coordinates equal to x, y, and z, set it equal to our values that we use farther up here for L1, and you find that lambda equals 2 for all 3 values. Okay, part D. It gives you point B as -1, 0, 2, and tells you it lies on L2. So you have to write down PA and PB, the different vectors that you have here. So P of A is you take point A minus point P, and you get negative times the direction vector of 1, 2, 1, which makes sense because it's the direction of L. You're going from P to A, so that should be the same direction as L1. Similarly, that should be the same thing for L2 when you have PB, so you take B minus point P, and you get negative times the direction vector of L2, 5, 6, 2. Okay. E is giving you the point D and gives you a parameter for point D. Point C is on L1 and point D is on L2. So it's asking you to make a from point A, B, C, and D here. So that's I shaded that in there to show that's the quadrilateral we're trying to find. It's really hard to find the area of a quadrilateral doing just the area of that. So I broke it up into 2 triangles. You can take any diagonal here. I chose the diagonal from A to D. So you can find the area of this triangle and add it to the area of that triangle. This formula is in your formula packet. So you have the area is equal to 1/2 times the magnitude of the cross product of 2 sides of one triangle. So I have AB times BD plus 1/2 the magnitude of the cross product of two other sides of a triangle here. So I have AC and CD. So both triangles will have their area taken and then added together to have the area of the quadrilateral. So first we have to find point D, and point D gives us the parameter -2 for mu. So we plug that into our values for L2, and we get -11, -12, and -2. So now that we have point D, we can find the direction vectors AB, BD, AC, and CD. So for AB, you take point B, subtract from A, and you get -4, -4, and -1. BD is similar, you take D, subtract B, that's the answer that you get. Same thing for AC and CD. So these four values are what I plug in for this formula that we got from the formula packet here. So you find the cross product of AB and BD. So these two values are going to be taken the cross product of. And then for AC and CD, the other triangle here, you take the cross product of AC and CD, put them right here. You get these two values, 4, -6, and 8, and then -12, 18, and -24. To find the magnitude, you take the square root of each value squared. So 4 here would be 16, plus 36, plus 64, and then same for the other cross product vector as well, for 144, 324, and 576. We still keep the 1/2 out front. We get our simplified answers. 116 is also the same as 29 times 4, so we can pull that 4 out as a 2 and multiply it by the 1/2. And then 1044 is also the same as 36 times 29. And you can do this by doing a simple factor tree. I just didn't show that work here, but just so you guys know where I got the answer from. So you can pull the 2 and the 6 out from the rad 29s. You have the similar rad 29s. So 1/2 times 2 is 1, and 1/2 times 6 is 3. So then you have root 29 plus 3 root 29 gives you 4 root 29 as the area of the quadrilateral. And that's the entirety of question 11.